Swayam Prabha. Digital India. Educated India.
So if we revisit and try to see what way we can overcome this problem, our major goal here would be that we want to alter the TCP so that we can achieve low latency communication and also be able to adapt at a very small time scale. But we want to ensure that the queue buildup in the first place doesn't occur so that there is no queue and no congestion that we can lead in. And we want to work with shallow buffered switches. That means we are not expecting the switches to have more buffers where the queues would build up. If the queues build up, we would end up having a lot of latency, and this latency would result in having for us to miss the deadlines. And hence, we want to ensure that we work with shallow buffered switches. And more importantly, when we think of the workloads, there are a lot of applications that readily use the TCP. So we do not want to alter or modify anything at the application space, nor do we want to change significantly any aspects within the switches or routers, because these are the devices that are going to be operating at the L2, L3 stacks. Without, if there are any changes, then that would mean that we would be customizing and requires a lot of efforts and costs in bringing these things up. And so equally important goal is to ensure that there will be no modifications at the application level at either ends of the devices, host devices that communicate, nor at the network stream in terms of the switches or routers. And the research in this direction led to some of the key ideas where we would want to address this problem. And one of them being to scale the window in proportion to the congestion. So whenever we have a congestion, the problem is we react only to the packet loss. And if there is a means to react much early and adapt our mechanism of how we transmit the packets, and even before the congestion actually sets in, we want to react, and that way we could basically mitigate these packet losses or retransmissions that end up taking a lot of time. And to do this, we had seen earlier in the transport layers that we can either use the packet drops using the TCP red, which would proactively drop the packets even before the queue gets full, or we could use the explicit congestion notification as a scheme where we could, instead of dropping the packet, we mark the packet and send them back to the sender so that he can react as if there was a packet loss and lower the rate at which you transmit the packets in the next round trip time. And this ECN readily helps ensure that without even having to experience the packet loss, we could react from the sender side and slow down the number of packets that we would send into the network. And this has been experienced and has been seen to work exceptionally well for the internet case. Then where's the concern of applying this in the data centers? And the only concern here is the reaction happens in a round trip time. And we are talking of round trip times on the internet in several milliseconds orders, 300 to 500 milliseconds and more, while in data centers, these would be in the microseconds space. And this is to our advantage that this round trip times are very short in data center, and we could use this to adapt very quickly in a microseconds time scale. But then with the traditional ECN, what we see is it's a single bit that's being added, which either slows down the sender or makes the sender to ramp up as you would otherwise do. So it's necessary now to understand how this ECN works and then see what's the problem in adapting this as it is to the data center networks. So if we think, let's consider a very simple topology as the source and destination connected via two routers. And whenever we have these source and router destination connect over this, they would basically exchange a series of packets from source and destination, at which each of the router that would see what is its current status and accordingly update the state on the packet that is sent towards the receiver. And if there is no congestion, the router would send the packet unaltered without marking any of the bits. And if there is a congestion at a particular router, then it would mark up the ECN bits in the IP header of the packets and then transmit it to the receiver. And once the receiver sees that the packets that it received were marked with the ECN bits, it would basically send this information back in the acknowledgement packet that it would send to the sender. And this, once it is received by the sender and sees that there was a ECN flag that was set, that means now there was a congestion perceived at the transport layer. The sender would understand that there was a congestion signal, and then he would slow down the packet rate at which he would send the next set of packets in the next RTT. And that's how the host TCP reacts to the congestion signal and ensures that the rate is slowed down when it sends the packets in the next RTT. And thus, without any packet drops, we are able to ensure that the congestion is being worked out from the sender side. But the problem here is that this feedback is completely binary. What that means is if any of the packets that you receive end up seeing that there is a ECN marked bit, then you would react. That means over a 1 RTT, even if I receive just 1 packet or 100 packets with the ECN marking, I react in the same way. And that means there is no concept of proportionality with respect to the number of packets that were marked ECN. And the way I would react is either that everything is fine and I would ramp up as usual, or I slow down and result in a data, basically making the next round trip to be slow by basically cutting down the congestion window by half. And this experience would say that now we would end up having a lot of aberrations in terms of how the transmissions would happen. So in DC-TCP, what the essence of bringing, like how we could adapt this for data centers, was brought out to see if we can extract this feedback, which is a single bit ECN mark, and extrapolate that to make it a multi-bit information, or basically trying to treat several of the single bit informations of the ECN marks to accumulate and create a multi-bit feedback mechanism. And to think of, we could do this by saying, if I receive n number of packets that are ECN marked over a given RTT with m number of packets that were actually sent, then I can use that fraction to say how much is the congestion really at the given instance and how should I react. Rather than completely reducing the congestion window by 2, I would reduce the window size based on the fraction of the packets that were marked in a given RTT. And this way, you would be able to adapt how much you would go in a slow, like how much you would ramp down rather than ramping down all the way to 50%. And this was exactly the core idea of DC-TCP. To put it in perspective, if we see that there were a bunch of packets that were exchanged, that is 10 of the packets that were sent in a given round trip time, and on the sender side, if it sees that there were, of the 10 packets that it sent, it received basically 8 of the packets were marked with ECN out of these 10, then you would want to react differently, as opposed to saying if there were only just 1 packet out of 10 that were marked with ECN. And if it were the default ECN and TCP that we use, in either of the cases it would cut down the window by 50%. But now our idea is to utilize these single bit information to make a multi-bit feedback, and we can readily do that by saying my congestion that I see is basically 8 out of 10 packets have experienced the ECN. That means the congestion is in fact bad. But how should I react to this information? And that we can do in proportion to the number of ECN bits that are being marked. So if I see that I had these ECN marks of 8 over 10, the way I would want to cut my window is basically saying I would do this with respect to saying, instead of cutting the window size by half, what I would now do is basically cut the window size in proportion to the number of packets that I received as ECN marked. So this way, what it would really result in is basically saying that I want to cut the window not by half, but basically in 40%. So if I make this in percents, so I basically reduce the window size by 40% of my current window so that I slow down and send, but not completely slow down to 50 and cut to half. And likewise, in the lower case, when we see that the congestion is really indication of saying if there was a microburst, which resulted in only one of or the other of the packets to be marked as perceiving the congestion at the router, I could basically see again and do that in proportion to the number of packets that I just transmit. And that would be half of the 1/10 of the packets that we received. And that would mean that we would cut down the window by just 5% and not 50%. And now if we see how this really, the reaction would look in terms of when we see the window size variations that happen in this TCP versus the DC TCP, we would see that in the regular TCP, you would have a ramp up, and then because of a packet loss, you are slowing down, cutting the window by half, and then ramping up again, and the typical sawtooth that we would see. But now, note that this is happening because we are always cutting the window by half. And instead, in the DC TCP, what we really care about is how much of the ECN packets that we really received. And if we received a very small fraction, then the amount of window that we would ramp down to is much smaller, like around 5%. And within an RTT, if we are sending a lot more packets, 100 or more, then you get a better scale in which you are able to, like a finer scale at which the window size would also be reduced. And thus, DC TCP ensures to not have the issue of having to fall down to very small and then ramp up again, while try to mitigate the aspect of how the congestion would be contained, and you are able to react. In fact, using the ECN approach helps us react much more quickly. And to put this in terms of an algorithm and see how it really works, on the switch side, it would be a usual ECN switch where you would just configure the parameter k, which says if any time the queue length increases at the switch beyond this threshold of k, you would mark the packet with ECN. And if the queue becomes full, and the only way is to drop the packet. But the notion here is that once you set this value k, any time a packet arrives and it has exceeded the queue length of value k, you would mark that packet and forward it to the destined receiver. And if any time the buffer size is lower than k, then you wouldn't mark, and it would be considered as a normal traffic. And on the sender side, whenever you would receive the packets that are going to be marked with k, he would keep track of how many packets within a given RTT were sent and what is the fraction of the packets, the fraction f here, to say how many of the packets that he sent and received in this RTT were marked with ECN flag. And if there is any mark of that ECN packets that he received with the ECN flag being marked, then we would want to react and adapt the window in proportion to the number of packets that we would have received. So the receiver echoes the actual EC bits back to the sender, and the sender accumulates all the packets with the EC bits to estimate first within each RTT what's the fraction of packets that he received, and use this fraction of packets as an information to say how much we should be adapting the window or lower the window. And if there is no congestion, no packets that are being marked, we can see that the fraction alpha would always basically be 0. And what that means is we would always honor whatever the traditional TCP in terms of ramping up. As alpha becomes 0, you are only going to be using g times of the aspect to say it's a traditional TCP approach of increasing the congestion window if you are in a slow start phase, or if you are in a congestion avoidance phase, it would again accordingly increase the window size over the RTT. But if there is any time we see that there is a packet that is being received with the ECN flag, then we would want to adapt the congestion window. And this is where we use this running average, that is the alpha variable, which indicates by how much should we take into consideration the current aspect. Because many a times when you transmit the packets that you send in one RTT may overlap with the packets that you receive in other RTT. So we don't want to just make the decision based on the current RTT afresh. We want to keep the information in a history and do that using the weighted average approach that we typically follow in TCP. And the weight G can be defined to say how much of the history we want to remember and how much of it that we want to react to the current instance. So if we say that G is a very large value, then we are reacting more impulsively to the information that we receive in a current RTT window. And if G happens to be a small value, then we also take into account in equal essence 1 minus G, the factor would pronounce in terms of what's the running average that we are having, and take into account the history or hysteresis of what's gone in with respect to the adaptation, and account the current window and past windows information in deducing what should be the window decrease. And this is a very important characteristic, because whenever we said that there will be information that we want from the workers to be sent out, they should be able to react based on what's what was observed earlier rather than what would be observed now. And that essence can be brought in by maintaining this G, and arbitrarily a good value of 0.4 or 0.5 would ensure that you are able to keep the history information and then accordingly send. And if we see that when a small history, a very large history can even tell us to say that we should slow down even before sending the packets upfront. And that's more desirable when we saw and want to understand how the incast can be addressed in a correct fashion. And this is a very simple algorithm, very simple mechanism, and we can see that there is no as such any tunings that are required specifically for the switches, in terms of, because the switches were already capable of having the RED or RED, random early drops, as well as ECN marking. So the same can be leveraged as it is at the switches. And very little has to be done on the source side, because source is now, instead of trying to react quickly, it is trying to accumulate over the RTT and then react. And this is a change that would happen at the transport layer, like within the TCP protocol. So the applications would again be agnostic to the kind of change that you would bring in at this TCP layer. So these changes could be readily adapted for the TCP in the transport stack of the source and destination sites, and it's only the source that would maintain this information. So the only new parameters that we are adding, that this information adds, is maintaining a running average of the number of packets that are being perceived as a multi-bit information, and then change in how we react to the adaptive window. And note, if this alpha is 0, then there is no change whatsoever to the traditional TCP approach. And if we don't want to react, we want to react to the ECN as in the earlier indication, then we can have G as 0. That means you're always trying to react with respect to whatever is the current information that you see, and you can again make it as a 1-bit information. And this decrease factor that we are trying to bring is always like half to less than half, and that's where this reduction of window would be like W to W by 2. Any range in this we can get in a small time, fine-grained steps, which would depend based on the fraction of the packets that we would want to use and the decrease factor that we would want to set. Thus, this fine-grained adaptation of reducing the congestion window in a very finer scales than just ramping down by half ensures that you have smooth variations for the congestion window, and this smooth RTT variations that ensure that we are able to operate with shallow buffers in a much more finer sense than reacting in a manner of TCP. And to put this in perspective and try to understand what really happens when we try to compare the DC-TCP with the traditional TCP and RED approach, the paper shows several of the evaluations, but I'm trying to put in the key aspect that would help us understand and distinguish the benefits that we see from DC-TCP. And if we observe, like they had a Broadcom router, where they would observe basically what's the queue occupancy for a given set of packets that were transmitted. So if we had one flow that's run over a long enough instance of time, just to show the benefits that this DC-TCP would bring, and try to compare that with the TCP RED variant. And we can see here from the figure on the left, for all the dotted lines here correspond to how the queue length was perceived by different fraction of the packets as they were transmitted out of that switch. And here you can see that for almost the 30% of the packets had observed around nearly 100 kilobytes of the queue length that is being set. That means if you consider 1 kilobyte packets, there are already a queue size that is built up of about 100 packets before they could even be transmitted. And only for a very small 0.1 to 0.2 is where the queue build is much smaller, right? Less than 10 packets. But as we go further, if we consider around 80% of the packets, you would see that there were more than around 200 packets at this point, with 200 KB of the queue length that's being utilized. And if you go further, more than 90% of the packets experienced to see that they were already queued up at well above 200 KB. That means the packet would only be delivered after 200 KB of the queue is drained out. That means it would be the 200th plus packet to be sent out from that link. And this essentially results, if you had a very small RTO, you would end up doing lots of retransmissions. And if you had a large enough RTO, you would end up missing the deadlines and ensure the packets would reach in a stale fashion. And as opposed to what we see with the DC-TCP approach, where the packets are now being sent, and if you see the cumulative fraction of the packets that experience towards the queue length as they go, you can see that up till 20%, you both experience the same amount of packets. There is no change. But beyond that, when the K factor that's being configured kicks in, you would start to see that the reactions are much more quicker, and every packet that is being transmitted for a given flow as it goes, it would not observe the queue to build up drastically at the switch. And all of the, even at the 90% or 99 percentile of the time, we are observing that the queue buildup is less than 100. That means the amount of time that it would need to drain the queue out and have the retransmissions done, you're reducing the chances to retransmit the packets because you are trying to meet the deadline. And most of the packets would then, whatever have been sent, would be delivered within the deadline. And this measure of the instantaneous queue length also we can see in the case of the TCP with red, you can see a lot of aberrations. And that's because whenever you see there is a loss, you would wait for the sender to slow down and then send. That would happen over RTT time, and the RTTs being very small, you would see that the sender would not react in a very quick fashion, and it would ramp down pretty quickly, making the packet instantaneous queue lengths also to go down much more rapidly. While with DC-TCP, what you would see is we are not cutting down the packets in the same proportion. We are not cutting down the window size by 2, rather we are cutting down in the proportions of how the congestion is observed. So it would follow not as much drastic drop, because even if we have to operate in a coarse and fine time scales, our adaptation is much more controlled, and in that way you would see that the queue length on an average is maintained between 50 and 100, and rarely it would drop in the cases where there is only one of the flows, maybe where it experienced and it has in the slow start phase and it ran down to the 0. So in a nutshell, what we see here now with this queue length visualization of how this has achieved, we can see that the TCP flows would experience less of a congestion as they are trying to react much more quickly to the congestion and ensure that the queue buildup would not go beyond the certain size where it would end up in having the delayed or make the flows to miss the deadline. So if we consider this experiment in a much more closer view, where there were 2 flows that were run on a Windows 7 networking stack with a Broadcom 1 Gbps switch, and you would see the queue lengths that would be maintained at the DC-TCP over a course of time as opposed to the queue length that would be maintained by the traditional TCP, you would see that the DC-TCP is maintaining almost a very small value of queue length, wherein you can see that throughout the DC-TCP was able to maintain the queue length at a switch at around roughly 30 kilobytes, where very small aberrations around this 30 kilobyte range. While this typically means roughly around 30 packets of 1 kilobytes that you would be basically having to transmit the packets at the switch. While with TCP, you can see that the queue length measured goes all the way up to 600 kilobytes, and it might drop all the way to less than around 200 kilobytes. That inferring that with the ECN approach, we are trying to keep the buffering consistent and trying to keep the buffering smooth at the switch without having to add any additional delay. And in a way, you are trying to keep the buffers empty to an extent that you are not overflowing any time and not conceiving any loss. And that's the most important aspect that we need to address or mitigate the incast problem. And thus, we can see that DC-TCP helps mitigate the incast problem by ensuring that we are creating a large headroom to accommodate the bursts. Right? So we are now saying that we can accommodate a burst of packet, but not an average queue that exceeds for a larger duration of time to take more packets. And that's the most important characteristic, because the main intention for us was to ensure that we can absorb the microbursts without having to have the real losses. And this is exactly where the DC-TCP helps. And if we compare now from an end-to-end application point of view, how this really results in terms of the flow completion times as we vary the flow sizes. And if we see that DC-TCP is more applicable in the aspect of when we have very small flows or the mice flows, and we wanted to give the advantage to the mice flows in a sense of trying to complete without having to experience much of losses. And we can see that for the 10 to 100 kb flows that we are seeing here, the flow completion times are almost half as opposed to what you would see in the regular TCP version. That's basically 9 milliseconds is what the DC-TCP took for completion of 10 to 100 kilobyte flow, as opposed to TCP taking around 16 milliseconds. And as we increase the flow sizes, making mices to move towards the elephant flows, we see that there is no adverse effect either. Like when we increase the flow size from 100 kb to 1 MB range, we are still getting the better benefit of DC-TCP in terms of having better flow completion time, but although in less proportion as opposed to what we saw with the 10 to 100 kb flows. And as we increase further to 1 to 10 MB, we are entering into the elephant domain where all the flows are now large flows, we would see that the TCP and DC-TCP would start to behave the same. And that's understandable in the sense that now we are keeping just the sufficient amount of packets in the queue, neither more nor less, but the links are always going to be occupied in terms of delivering the packet. So there is nowhere where the link would starve of the packets, and it would have just sufficient number of packets in the link to send the packets out. And likewise, we would see that when the flow size increases further, TCP and DC-TCP would almost behave the same way. So the takeaway here is, with TCP, what would happen because you react in either cutting the congestion window by half or reacting you are basically making the queue at the switch to starve and not accommodate the microbursts. And with DC-TCP, on the other hand, what we have ensured is that the buffer occupancy at a queue is contained, and it will be sustained at a value k that you would configure. And by doing that, you have built the headroom to accommodate microbursts at a given time where the packets can still be accommodated within the queue, and only if the queue length increases, the average queue length increases for a duration, then they would be marked. And you would, whenever there is a marking, you are not reacting instantaneously either to cut down the window by half. Instead, we are jumping in proportion to the number of packets that really absorb. That means if there were a microburst of packets, you would experience 1 out of 10 or 1 out of 4 or 5 packets to say that we would react accordingly. And thus, you are able to ensure that we are not having any overheads at the queue in terms of overflowing the buffers, providing them a space to accommodate the microbursts, and at the sender side, you are able to react in a proactive manner and send just the right amount of packets that a queue would handle. And thus, this DC-TCP is able to ensure that provide the better benefits, especially with respect to the mice flows. And on the right hand side here, what we are trying to see is the query completion times, which is an end-to-end applications where you are trying to make the queries and see how they really behave. And we can see that these queries typically include basically lots of the short flows. And the effect is, in essence, when you look at the higher percentile of the queries that complete within a given time. And you can see that most of the queries with the DC-TCP are able to complete, even 99.9 percentile of the queries were able to be completed within 40 milliseconds, while with TCP, the numbers jumped up to 68 milliseconds. And thus, we are able to contain the time and meet the deadlines in a soft approach using this DC-TCP as a protocol. So to summarize, what we have seen is the way DC-TCP works is that first, it ensures that there is a low latency for the communications between aggregators and workers, or all in for that matter, any of the nodes in the data center. And that is possible because of small buffer occupancy that is being ensured by the use of the ECN marking approach, and ensuring that the quantized bits of the ECN that are being considered when you receive the multi-bit factor, you are reacting much more slowly, much more not aggressively, but much more in a fashion of in proportion to the perceived congestion. Second, that it ensures to keep the high throughput, because ECN is an averaging and the smoothing factor helps ensure that you are able to accommodate microbursts and not experience any packet losses. So you have, in essence, minimized the packet losses that otherwise would occur when the queue would be more or less full. So because we have contained to a smaller queue size, we are able to accommodate more and more of the bursts. And because we are able to accommodate more and more of the bursts and ensure that the links can send the packets consistently, you are also able to ensure that we get high throughput. And also ensuring that we will have very low variances, because the sender and the receiver need not react much more quickly or aggressively and ensure that the packets are sustained within the queue. And this high burst tolerance is a most important aspect because of the large buffer headroom, ensuring that many of the mice flows, when they come, they will often result in many of the bursts, and we are now able to accommodate them. And the marking approach has not changed in terms of how you would mark with the ECN. You would do that, but you can mark it much more quickly, and you can even, in fact, do aggressive marking to ensure that you are able to react much before the packets are dropped. And these aspects ensure that DC-TCP works in this data centers in a much better fashion than the transport layer protocol in a traditional transport TCP. So to summarize, the key benefits of DCP is the better performance in terms of low latency and high throughput, and it alleviates the losses that can happen due to the buffer pressure at a queue, at a switch, because we are now able to contain several of the microbursts. And it also provides a means to quickly adapt to the congestion for the end hosts in terms of how to react in a much more controlled fashion than in aggressive fashion of reducing the congestion window. And most important is that because it doesn't require any additional changes at any of the network elements, nor at the application layer, but just the TCP stack that we can build in the Windows or Linux network stacks, this becomes readily deployable and a very practical solution in addressing the TCP incast. But I do want to caution that this DC-TCP is a better approach of handling the incast, but in essence, this doesn't solve the incast problem as it is. And if we have to really address the incast problem, what really requires, wherever we asked about the switches that are having the buffer sharing, we want complete isolation of the large elephant flows and the small mice flows. And this is something that is only possible if we address at the scheduling of the packets and marking of the packets as either elephant and mice, and accordingly handle the packets, which is not the intent here that the DC-TCP does, but it does in generalized way to accommodate microbursts. So there were a lot of other works that came after this in terms of what were the shortcomings in this DC-TCP and what are the means to do this by using better packet scheduling approaches to work around the TCP incast. But for this context, we will stick to this DC-TCP, and you may follow several of these works that came, including several of the work from Google and Facebook, Timely as one of the papers that came in 2017 SIGCOMM, and DCQCN approach was another Microsoft approach, in fact, where they tried to improvise on this approach of DC-TCP as a means to address the congestion problems. So there were several other works, interesting works to look at, but for the scope, we will contain here, and hope we have gotten a good understanding of how this DC-TCP works and why there was a need for a variant of TCP to be set up for the data centers.